First, I'd like to thank the organizers for this invitation. It's a great pleasure to give this mini course.
Yes? Excuse me, Lucy. We don't see you. We don't have. Oh, now it's good.
Okay.
Thank you.
So I should stay here and not there. So this mini course is, well, I'm not really in foliations, but I'm going to talk about a subject which is very important in geometry and complex and real geometry. And so it is my belief that this kind of subject could be of use to people in foliations also. So I will be talking about real forms and real structures of complex varieties. In this course, today I will just do a classical setting where we just look at complex varieties and define these objects. And then in the next courses, I will add a group action and talk about the equivariant version of this subject. And my goal is to state some classical questions and some relatively new results in some of the parts of this subject. So for today, where there's not a group action and it's just definitions, I think what is important is the way I define real forms and real structures. There are many different ways of doing it, and I will set up a structure which is well adapted to what I want to do here. And I hope that it convinces you that it's a good way of looking at real structures and real forms. So for today, the references that I would give would be a book by Frédéric Mangold. It was originally in French. It's now translated into English, and it's called Real Algebraic Varieties. And Frédéric Mangold had a thesis student in 2016. That is only in French, but it's a very nice work where the description of real algebraic varieties is given very clearly. His thesis was from 2016. The book was originally written in 2017, I think, but the English version is in 2020. Okay. So this is just to settle the definitions and what I will talk about today. So I'll start by giving a definition of a real structure of a complex variety. So the definition is as follows. If X is a complex algebraic variety, so it can be affine, it can be projective, it could be quasi-projective, it can be whatever. But it's I will define a real structure on X is an anti-regular involution on X. And what I mean by that anti-regular is such that if I'm gonna do it with brutally here, and then I'll describe what I mean. I look at X, I look at spec C, which is just a point, and I look at the map that comes from Z goes to Z bar. That means that it's anti-linear. And I want this map to commute. Okay, so that's a little weird to say because this is just a point and this is just a point. But I want the structure of C to be the same. So I'll say it in a different way so that to be clear that everybody understands what I mean by that. So, in other words, I'll do, in other words, in the case I'll take the case where X is affine. So it's an affine variety. It has a coordinate ring. And I'll define a real structure on the coordinate ring is just is given by an action of the Galois group gamma, which is the Galois group of C over R. This Galois group contains two elements, one and another element I'll call gamma. And I want it to be such that gamma on C is just given by bar of C. Okay. In other words, I want, that is, gamma is a ring homomorphism, ring automorphism, and gamma is a ring, induces a ring involution on Cx such that gamma applied to Cf for anything, it's just C bar gamma F. Okay. So that's what I mean by anti-regular. On the complex numbers, it's just bar. Okay. So I'll give you some examples. Let me just make sure that I'm not, what did I do here? Okay, I started here, I'll put here. Okay, I'll just, well, before I do that, I just want to say, okay, this is on Cx, and I'll say this action, this induces a gamma action on X. Okay, because I have it on the ring. Okay, so I'll just give some examples. Okay. Well, the first example, it'll be very easy. Affine space. Okay. And I can say mu of Z1 to Zn just gives me Z1 bar to Zn bar. Okay. That is that's a real structure on this affine variety. On the ring of functions, what does it do? It's mu of any polynomial C I1 to In, Z1 I1 to Zn In. It'll be the sum of Ci1 In bar, Z1 I1, Zn In. Okay. It just changes the constants, doesn't do anything else to all the other variables. So this is a typical real structure on affine space. Okay, let's do one where there's something actually interesting that happens. I will take complex sphere. So I'll take X is, okay, how did I write it here? I want to use the same notation, yes. So it's the it's the real variety coming from 3 variables such that x squared plus y squared plus z squared equals 1. Okay. It's a complex variety, which we often call the complex sphere, because it comes from this. It has several different real structures. Let's just look at some more. I can take mu1 of x, y, z. Can be x bar, y bar, z bar. But I can also do mu2 of x, y, z. Gives me y bar, x bar, z bar. Okay. Now, is there something? But both of these are involutions, and I claim that they look very different. Okay, so I have to define what that means. I'm going to say 2 real structures. Okay, so in definition, 2 real structures mu1 and mu2 on x are equivalent if one is conjugate to the other. That means there exists phi, an complex automorphism of x such that phi mu 1 phi inverse equals mu 2. Okay. Okay, so that's a definition, and what I claim that these 2 are different. These are not equivalent. Okay? And the way I will show it is by looking at another way of looking at this thing. I will look at real forms and real points.
We can't see very well here. What's the idea of defining it is x squared plus y squared plus z squared minus 1?
Yes, a sphere.
There is no sign. Okay.
X squared plus y squared plus z squared minus 1. Yes.
Yeah, but then if you take phi as just the permutation of x and y, wouldn't it be a...
That would be a real form, but what's going to happen is that these two will be different, and then many of them will be the same, will be equivalent. Like well, I'll show you, but there are different ways of, there are many different real structures on this, sphere, okay? And what will be different will be the set of real points. Okay, so let me just go on here for a second and then we'll come back to that. Okay, a real form of x of x is a real variety z. So that's a variety defined over the real numbers such that its complexification is just isomorphic to x. Okay. So what happens? If x is quasi-projective, and mu is a real form on it, mu is a real structure, then if I take the quotient, it will be a real form. just a real variety whose complexification is here. And the way that we've said it by construction, x mu1 is isomorphic as real varieties if and only if mu1 is equivalent to mu2. So my equivalence comes from saying I want the real forms to be the same. Okay. So what this means is that, at least in the quasi-projective case, giving a real structure is the same thing as giving a real form. Okay. There's a bijection between real forms and real structures. I'll put it this way. Real forms of X, real structures on X. If they're bijective, if I have mu here, I just go to the quotient. If I have z here, I just complexify. And so this gives me two ways of saying the same thing in the case of quasi-projective varieties. If the variety is not quasi-projective, I might have problems with this quotient because it might not be a real variety. So I'll just stick to the quasi-projective case where things stay nice. Okay, so now that's real forms, that's real structures, and then I can look at the real points. What are the real points? The real points is the fixed point set. It's the element that are fixed by x. Okay. Yes?
If I didn't get the overlay back, like if you have the real part.
If I have a real variety, I complexify it.
And what will be the real structure?
Sorry. What is the real structure? The real structure will be a map that fixes z and sends z to z bar. Okay. Okay. Yeah, it's not really written correctly there, but okay. But that's the idea. If I write it like this, I mean that I want mu to fix the elements here and not here. Okay. Okay, so I have my real points here, and what happens is that if mu1 and mu2, mu1 and mu2 equivalent will imply that these fixed points will be diffeomorphic. And so if I want to show that two different real structures are not equivalent, one way of doing that is to show that their real points are not diffeomorphic. Okay, where's my example that I wanted to put here? Do I want to put it after? Yeah, I'll do it a little bit afterwards. Okay. So one classical question is, given a complex variety X, what are all the equivalence classes of its real forms or real structures? So I'll do that. determine all real structures up to equivalence of X. Okay, to do that, there are two things one has to do. One is existence. Is there any real structure? I won't talk too much about that today, because the examples I give will have an obvious real structure, and what will be more interesting to me is the second part. If one real structure, if at least one, exists, how many are there? What are all of them? Or how many are there? Now, this is a classical result of where the way one can figure out how many there are is with a cohomology set. So we suppose mu 0 is a real structure on X. And we consider the action of gamma on complex automorphisms. And the one I'm going to pick is one given by conjugation by this mu 0 that I've given. Okay. Okay, phi. Okay, so gamma sends phi to mu, phi, mu. Conjugation by mu. Mu 0 is an involution, so this is conjugation. Mu 0 is anti-regular, phi is regular, mu 0 is anti-regular, so this is regular. Okay.
Sorry,
What's the question?
What is gamma? You say consider the
Gamma,
action of
this
gamma.
is my group gamma has identity and this one other element, gamma. I have gamma is the Galois group of C over R. It has two elements, the identity and gamma. So I just have a Z2 action where this is my involution. Okay. So how can I, okay, so this gives me, if I have mu 0 fixed, I have an action on this group. I'll give you some examples in a moment. And then I can say the set of the real structures will be given by phi mu 0 such that phi, okay, well, let's put it like this. Any real structure mu 1 on X is of the form phi mu 0, where phi mu 0, phi mu 0 is the identity. Okay. Anytime I have a real structure, I'll put it here. In other words, if that is, if mu1 is a real structure, then I can say mu1, mu 0 is an automorphism of X. Okay. So I can always write it like phi mu 0, but I have this condition because I want it to be an involution. And what is this condition? This says phi times the action of gamma on phi is the identity. That's just exactly the condition of being a cycle. So I'm looking for all these automorphisms such that phi mu 0, phi mu 0 equals identity. This is just the one cycles in the group gamma to aught X. This is gamma of this element here. And when are they equivalent? Okay. Phi 1 gamma, phi 1 mu 0 is equivalent to phi 2 mu 0, if and only if. Well, there's got to be an automorphism, so there exists a psi in the automorphism of C of X, such that psi inverse phi 1 mu 0 psi and psi should be phi 2 mu 0. But what does that mean? I just move the things around. That just means that psi inverse phi mu 0 psi mu 0 equals phi 2. This is psi inverse, and this is acting by gamma on psi, and this gives me exactly the equivalence. Defines the equivalence, giving H1, sorry, H1 of gamma aught X is simply Z1 of gamma aught X modulo this equivalence. Okay? So it's just a terminology, it's a way of saying how to find all real forms. What I need to do is look at this automorphism group and look at all of its the elements of this form and when they're equivalent. So I'll give you some examples to start. We'll start on affine line. There we know very well the automorphism group. It's just affine linear things, and it's not hard to show that up to equivalence the only real structure is X gives X bar. There, the real form is just the affine real line, and the real fixed point set is the real line is here. So that's for A1, that's easy. Two. When affine 2 space, it's the same result is true, but it's much harder. Okay? The group of automorphisms here is known to be amalgamated product of the triangular and the affine linear maps. So one finds here also only one real structure. So this is a result in 1975 by Kambayashi. What happens for n higher, we do not know. We do not know if there are other real structures on AN3. So I'll write this question in a different way, just for n bigger than or equal to 3, we don't know. So a way of saying this question is let A be a real finitely generated ring such that when I take A and I tensor over C, I have a polynomial ring of n variables, and at least 3. The question is A isomorphic to R x1 xn? Surprising to me that we don't know that answer to that. But we don't. The reason it's difficult is because the group of automorphisms of affine space starting at n equals 3 is very complicated. Okay. So let me go back to another example, which will be more important to me. Yeah. Where? No idea. No. People think, try, play. I've played a lot. It's not, but I think many people have. And well, it's difficult because, well, you need to have other ones, you have to have the automorphism group has to be big enough. But then when are they equivalent? Okay.
We didn't listen the question. What was the question?
The question is here, do you see the question here?
Not the one that you made, but the one that the person...
He asked if I had a guess of which way, what is the answer? I don't have a guess. I don't know if it's true or not. I have no feeling of why it should be or shouldn't. Okay, so those are affine spaces. So now let me go back to my complex sphere. So I'm going to write it C, X, Y, Z. Coming from the usual, this one is a usual way of writing it. And this way, I'm going to write, before I was doing structures, just to do it a little differently, I'm going to do it with real forms now. This up to equivalence there are 4 real forms of this. And what they are, they come from spec R, x, y, z, x squared plus or minus y squared, plus z squared, plus or minus 1. And I claim they give me 4 different varieties, and they are all different. They're not equivalent. And to see they're not equivalent, one can look at the real fixed points. If you say plus with a minus here, then you get a real sphere. If you say x squared plus y squared plus z squared plus 1 equals 0, you get the empty set. That's the real set, a set of real points. If you say x squared minus y squared plus z squared plus 1 equals 0, then I just pick x and z however I like, and I have y, and I get 2 copies of R. Okay, it's disconnected. And finally, if I have x squared minus y squared plus z squared minus 1, I get a cylinder. So they're all topologically different, which means that the real forms are all different, or the corresponding real structures are all different. One has to work a little harder to show that there are no other ones, but it's not too hard. So for something like that, we know. And I will, well, I doubt it's today because I see the time going, but I will be interested in 2 special cases of this variety here. I will be interested in the real sphere and the cylinder. Okay. So I'm going to rewrite these 2 varieties. So S2 over R with respect of R x, y, z over x squared plus y squared plus z squared minus 1, and H with respect of R. I'm going to write it slightly differently, uv and z, where uv plus z squared minus 1. U is x plus y, v is x minus y over 2. Okay? And so these are 2 different real varieties whose complexifications are the same. Not surprising. A hyperbola, it's like a hyperbola in a circle. Okay? Okay, and the last example I want to give here is not an affine one, but a projective one. I'll do projective space. Just this projective space. Okay. Okay, P, Cn. Okay. And I claim that it has 2 different real structures or real forms if n is odd and 1 real structure if n is even. And I'm actually going to leave this as an exercise for you, but I'm going to tell you how to do it, okay? So this is one that we can actually really calculate. The reason is we know the automorphism group of P and C. Okay, the automorphism group is just GLN, see, modulo, so PGL. Okay, under PGL. So if I want to find a real form, that means find a matrix. So I have my obvious one. I have Z0, Zn, which goes to that's one real form always. And then now I look at the automorphisms and see, can I compose that with an automorphism to get something different? And the answer is I can, if and only if n is odd, and I can then change this to minus z1 bar. Okay, I can make it go to minus z1 bar, z0 bar, minus z3 bar, z2, pardon, 2, 3, etc. I just, by pairs, I switch them and put a minus sign. It's easy to see these two are different because here the fixed point set is a PNR, and here the fixed point set is empty. So that is easy. So to see that for n being odd, there are at least two is easy. But then to show that that's all you have to look a little at these automorphisms and say, well, if you have an automorphism with this one, I call that the matrix of the automorphism will be A, and it means that if I go A bar, it's going to be a homotessy. And I have to look at that homotessy. So I'll leave that as an exercise, and we can discuss it tomorrow or in the otherwise. Okay, so that is a nice picture here. So the topic I want to talk to you about now is that, well, for many years, many people knew lots of examples of real structures, real forms of varieties. But what they didn't know is, can one find one variety that has an infinite number of different real structures? Okay? And the answer we know now is yes, but it's quite recent. So I'm going to give you a list of some different examples that were given. And it's the first example was in 2017 by Les Yeutres. And they're projective of dimension at least 6. Les Yeutres. 2019, Dean and Ogrizo gave families of examples, families of projective examples of dimension at least 2. So they brought it down. But in their examples, the idea is that they weren't looking for infinite number of real structures. What they were looking for was projective varieties with interesting automorphism groups. And these varieties that they construct have an automorphism groups which are discrete, but not of finite type. And because of the structure of these automorphism groups, they got, as a plus, infinite number of real structures, because the automorphism groups, they could show that when you have the discreteness of the automorphism group gives that. These projective varieties are not rational, and it's because of that about let's say, we'll say in 2019 or 20, I'll put 2020 to be precise. Adrien Dubelot, Jean Freudenberg, and myself gave examples where X is affine, rational, of dimension at least 4. Okay. So what's nice here is the rational. Soon after, Dean, Yu, and Oguizo made their results better, and they could get rational projective of dimension at least 3. Now, in all these examples, there's infinite number of real structures, but it's still countable. And the nicest result we have now, 2029, is of Anabot, who gave a surface. It's an affine surface with uncountably many different real structures. And this comes from Giza-Tulin surfaces. Now, I would like to describe, well, all of these results are quite difficult to describe. This one, I can give a sketch, and that's what I'm hoping to do probably the next time. I'll give a sketch of this proof. But so for today, I have still 3 minutes, something like that. Is that what I have? Okay. So I'll just set this up. I'll set up what we will do to make this work, okay? So I will tell you what hey, it was right here. Okay. I should have left it here. Okay. Well, okay, I'll do it differently. The variety that I'm going to pick, so it's just a sketch of this, of the affine result. Sketch of proof of D, F, and J. Right? So the variety I'm going to pick is going to simply be this complex sphere cross A to C. Can't get much easier than that. Okay? And what I'm going to do is think of this as a fiber bundle, where this is the base and this is a trivial bundle. And I'm going to put real structures on this variety in such a way that I will find infinitely many that are different, because the topology of the real points will all be not the not diffeomorphic. Right? Let me just say a couple comments, and then tomorrow I will give this result. So first of all, the group of automorphisms here is huge. There's no way that I can pretend that we have all of the real structures. There can be ones that mess up this fiber bundle structure. But if I look at the fiber bundle structures, there are reasons to think that I have all of them. Okay? Secondly, I will the ideas of how I'm going to do it tomorrow will be quite elementary. So, but behind the scenes, the reason that it works is because of very deep results by Murty, Swan. Let me just give you, I think that's what I'll do just in this last minute. I'll just tell you the results that they gave that are behind the scenes here. Murty from 1969 said that any rank 2 vector bundle on this space here splits into a trivial factor and a line bundle. Now, I, in the end, don't need it because I'm going to do it, but I would never have guessed that it worked without this result of Murty, okay? So that's one thing that we use. And another is, well, what we're going to do is we're going to look at vector bundles in 3 settings. Complex, rank 2 vector bundles, real, algebraic, and topological. And, well, there's a, how do we compare the real and topological? It's a result of, okay, that's the last thing I'll do for today, of Barge and Ojangoran. Okay, on the sphere, okay, Barge and Ojangoran tell me the following. All real forms. Okay, you take any topological vector bundle over the real sphere is realizable algebraically. They do more than that, but that's the part that's going to be interesting to me. So I'm going to look at the topological vector bundles over a sphere, compare them. I'm going to make them algebraic, and make that algebraic part be a real form of a complex one. And, well, that's for tomorrow.
Okay, thank you very much. Are there any questions?
Any question here?
Yeah, there's a question there. Yeah.
I don't think so. I think we can thank Lucy again.
Well, there's a
Oh,
question.
you have one?
Okay, so if I understand, the existence is always guaranteed.
The existence, I didn't say anything about here. That's another story.
Okay.
I mean, they don't always exist, but
Are there examples of complex variety with no real structure?
yeah, sure. Do some elliptic curve where there's too many complex things. I'm sure. Well, I don't have one offhand. I have many with group actions that don't. But yeah, I don't have one offhand. But you could certainly construct them with non-rational curves and something.
Okay.
Thank you. Maybe another question. If you consider mu0 given real structure, and you deform it by taking an automorphism which is in the component of the identity.
Right.
Can you find other
sometimes
real structure?
Well, they're often.
I was wondering if it is a question of connected components.
Well, I mean, the examples of Anna Bott, you can do that, but she's moving a point that she blows up, and that changes a little bit. So, well, I'm going to say that usually that does not work, and that's why it was so hard to find examples where there infinite numbers of them. But I think that it isn't clear to me that you can never do it.
Okay. So if there is no other question, so let us thank Lucy again.
Okay.